Remember the fundamental question from part 1? If we process our signal using digital signal processing techniques in the middle here, how does that affect the relationship between xt and y of t? Well, we're almost in a position to be able to answer this question now. What we are going to do is we are going to define a concept of frequency in discrete time, and a sinusoid of a certain frequency in discrete time will correspond with the same continuous time version of that sinusoid at the same frequency. This means that if we understand what our DSP block does in the frequency domain, we almost immediately understand what it does to the continuous time signal. So to move between discrete time and continuous time, we think in the frequency domain. Provided the input is band limited and we are sampling it fast enough, then there is a one-to-one relationship between a sinusoid in continuous time and a corresponding sinusoid in discrete time. If x of t is equal to e to the j omega t, then when we sample it, we get x of k is equal to e to the j omega k, in some sense only a very small difference. From what we said before, this suggests that if I can decompose my x of k, so x of k is just a sequence of numbers indexed by time k, where k is an integer. If I can decompose that as, for example, 2e to the j 0.2k plus 5e to the j 0.3k, where I've just made this up arbitrarily. But if I have this decomposition, then based on what we said before, that suggests that my D to A converter, when it converts the signal back, is going to give me x of t equal to 2e to the j 0.2t plus 5e to the j 0.3t. Indeed, when I sample, I go from the index t to the index k. Here, to go back, I just change k to t. You might say this is very arbitrary. I could write x of k as some other function involving k and then just replace k with t. However, the point is, if we were to do that, we could also decompose that function in terms of its Fourier components, and we would end up doing essentially the same thing. The difference is how different frequency components are handled. If we do it this way, then we have a very clear picture that provided x of t is band limited, we're going to recover it. And if x of t contains higher frequencies, they're going to get aliased down, which we'll discuss in a second. If I had an arbitrary function here, then it might mix and match. It might take a sinusoid and map it to a higher or lower frequency. It might even take a sinusoid and map it to several related frequencies. That, however, is going beyond the simpler fact that this way really does work, as we can verify in hindsight. Indeed, this trick that I just described, where we simply write our x of k in terms of these complex sinusoids and then replace k with t, this is exactly the same as our reconstruction principle we mentioned in part 2. The only caveat is that when we perform this decomposition, we have to make sure to write the frequencies to be the smallest possible values in magnitude that satisfy this decomposition here. To explain why, we will briefly talk about aliasing, and then we will return to this picture later to complete the picture. Here we have 5 points, and let's try to fit a sinusoid through these points. Here is one solution, and here is another solution. While you may well be skeptical of this poor diagram, we can verify what's happening mathematically. You can use sinusoids if you wish, but I prefer to use complex exponentials as they're a bit easier. So let's assume that my blue trace is e to the j 0.2 t for argument's sake, and we've sampled that. Now, can we get another curve, another complex exponential, e to the j, but a different frequency here times t, such that these two are the same whenever t is an integer? The trick to answering this is realizing that e to the j 2 pi and n can be any integer I like times t. This term here will always equal 1 whenever t is an integer. So I can fill in this spot here with 0.2 but leave the second term there to get that this is going to be e to the j 0.2 plus 2 pi n all times t. And from what we've just said, this signal here is going to be indistinguishable from our original signal at integer samples. Let's investigate with a specific numerical example. I am given a sequence x of k, and I somehow discover that I can write x of k as e to the j 5k. I can now find an infinite number of possibilities for my x of t that will equal x of k whenever t equals k is an integer. For example, I can choose x of t to be e to the j 5t. That's easy. But I can also choose it to be e to the j 5 minus 2 pi t, and that will also agree with my samples at every point k an integer. We have no way of choosing the correct x of t unless we understand about the application we're in. Why do we want to recover an x of t in the first place? Remember, our application is to process a signal x of t in the digital domain for convenience. So we therefore know something about x of t. Almost always we know that x of t is band limited. What this means is out of the infinite number of choices here, I am going to choose the one where the frequency is closest to 0, because that's what it means for x of t to be band limited. It means all its frequencies are closer to 0 than any aliased version, where here in this example, where we're sampling at integer times, an aliased version is a frequency that differs from another by an integer multiple of 2 pi. For this concrete example, let's look at all possible frequencies we can have. By assumption, we can have 5. We somehow observed that this fitted the data. But we can also have 5 plus 2 pi. We can have 5 plus 2 times 2 pi, or 4 pi, and 5 plus 3 times 2 pi, or 6 pi. And in the other direction, we can have 5 minus 2 pi, we can have 5 minus 4 pi, and so forth. Out of all these possible choices, because we know that x of t is band limited, we know that the choice must be the one closest to 0. And so we see x of t must be the complex exponential sinusoid with this frequency 5 minus 2 pi. Any other possibility would mean that x of t contains frequencies higher than it should. Remember, we were told x of t is band limited. How does that fit in with where we started? The idea is straightforward. If we can represent x of t as a sum of sinusoids, then when we sample it, we get essentially the same structure here, also a sum of sinusoids. We've just replaced t with k. In our DSP block, provided we only perform linear time invariant operations, we are going to preserve this basic structure here. We will modify the constants out the front, but we will keep our frequency components here. This means that once we finish processing our signal, which essentially just means changing these constants out the front here, to go through the D to A converter simply means replacing k with t. Because we've been careful to make sure that all these frequencies stay band limited, so to speak, we know that we can just replace k with t. The reason why they stay band limited is that if we perform a linear time invariant operation, it's not going to change the frequencies. Tangentially, if we are naughty and perform some other operation here, which is not linear time invariant, we would be changing the frequency components, but the same principle applies. To understand what happens when we convert it back to the real world, we would have to take our new frequency representation, make sure that all the frequencies here are as small as possible, as close to 0 as possible, and then we replace k with t, and that's what the output of an ideal D to A converter will be. So even if we're not doing linear time invariant operations, this is still key to understanding what's happening. First and foremost though, linear time invariant operations are already very rich. There are very many things that we want to do that are linear time invariant. So it already suffices for us to understand this system when this DSP block is a linear time invariant operation. And in this case especially, then it's very nice and very attractive to think in the frequency domain. We decompose x of t as a sum of sinusoids. We then understand the DSP block as just modulating the magnitude and phase of each of these frequency components, and then going through the D to A converter simply converts k back to t, which means, in effect, we have been operating on our original x of t all along. All our DSP block is doing is modifying the magnitude and phase of the different frequency components of our original time domain signal x of t. This way, suddenly this whole system becomes very transparent, very easy to understand what we're doing in the digital domain corresponds directly with what we're doing in the time domain. Once we have intuitively understood what's going on, it's quite easy to formalize it mathematically. We start with the inverse Fourier transform representation of x of t. This tells us all the different frequency components there are in x of t. Then, because x of t is band limited, we can change the limits of integration here to a much smaller range. We can work out just how band limited we require x to be. We can do this as follows. We know from the previous page that x of t equals e to the j omega t, and x of t equals e to the j omega plus 2 pi t are indistinguishable from their samples. What this means is that x of t cannot contain two frequencies that differ by 2 pi, otherwise it's impossible for us to recover x of t. So 2 pi is the largest distance between any two frequencies in x of t. Because we want things to be symmetrical about 0, this means that our limits of integration here need to be from minus pi to pi. By this I mean we are assuming that x of omega, the Fourier transform of our continuous time signal coming into our system, x of omega cannot contain any component outside of this region here. If it did, then we would not be able to recover it by assuming that x of t were band limited. Given this representation for x of t, we know immediately how we can represent x of k as a sum of sinusoids. Indeed, it's just given by the same formula, but with t replaced by k. Remember, when we sample, x of k is just equal to x of k times capital T, where capital T is the sampling period, and we are assuming our sampling period is 1, therefore x of k is just equal to the continuous time version of x evaluated at time k, where k is an integer. Therefore, we get that x of k is the same of x of t, where we just replace t with k in here, which is the only difference between these two equations. It turns out, as a good theory ought, that everything fits together very nicely, meaning that if I now look at y of k, it doesn't matter what this DSP block does. You can pick any sequence you like to be y of k, and I can always represent it in this same form here. Precisely, you give me any y of k, any sequence y of k, I can always find a function y of omega such that this equation is true. And this allows me to write y as a sum of sinusoids, all of them having a small frequency close to 0. The crucial fact about this representation is that I know that when y of k goes through this D to A converter, y of t is going to be given by this exact same equation, just with k replaced by t. That is the key point. Focus for a moment on this DSP block. Its input is x of k, its output is y of k. We can represent x of k in this form here. We can represent yk in this form here. So if we know what the DSP block does to x of k to get y of k, we can figure out what it does to x of omega to get y of omega. And that then tells us immediately what it's doing on our signal x of t to produce y of t. Remember, x of omega is just the frequency representation of x of t, and y of omega is just the frequency representation of y of t. We have come a long way towards answering our two fundamental questions. Fundamental question 1 was, what does this whole chain do to the signal x of t? And question number 2 is, if I wanted to filter x of t in some particular way, how do I design my DSP block here to achieve that? Well, this derivation here shows that we can understand exactly what the system is doing, how this DSP block converts the frequency components of x into the frequency components of y. This then reduces our two fundamental questions to questions simply about how this DSP block changes the frequency components of x of k into frequency components of y of k. This leads immediately to the introduction of the discrete-time Fourier transform. Specifically, these equations are the discrete-time Fourier transforms of x and y respectively. It's just customary to use a lowercase omega instead of uppercase omega when working in discrete time. To summarize, this is the inverse discrete-time Fourier transform of x of omega, but I always like to think of it as representing x of k by a sum of sinusoids. Naturally then, one may want to know, how can we obtain this x of omega given an x of k? Well, that's the purpose of the discrete-time Fourier transform. An ideal A to D converter simply creates a sampled version x of k of the original continuous time signal x of t. When capital T equals to 1, and if x of t is suitably band limited, then we know that x of small omega is just equal to x of big omega, with little omega equal to big omega. In other words, there is a one-to-one mapping between frequencies in continuous time and frequencies in discrete time. There is a simple way of remembering what happens when our sampling period t is not equal to 1. By convention, we are always going to choose k to be integer valued. This means that its frequency components are always going to be between minus pi to pi. The smallest frequency is 0, and the largest frequencies are plus and minus pi. On the other hand, if we sample x of t at a faster rate, we are getting more samples per second, we are getting more information about x of t, so we expect that we don't require x of t to be as band limited as if we sampled with t is equal to 1. In the t equals to 1 case, we have little omega equals to big omega, so to speak. Precisely, we have got this relationship here. The way we think of this is that a discrete time signal can only contain frequency components, angular frequency components if we want to be pedantic, between minus pi to pi. If we sample with t is equal to 1, then we require that in the frequency domain, x of t is band limited to the same region from minus pi to pi. This is because when t is equal to 1, we have a one-to-one mapping. A frequency of pi in the continuous time case maps precisely to the same frequency pi in the discrete time case as given by this formula here. If, however, we take t is equal to a half now, meaning that we are going to sample at twice the rate, then we expect that in the frequency domain, our original signal x of t can contain higher frequency components, twice as high in fact. It makes intuitive sense that if we sample twice as fast, we get twice as much information and so can allow f to have a bandwidth twice as large. This reasoning suggests that in general, the discrete-time Fourier transform spectrum is going to be equal to our original spectrum, just with the frequency modified by the sampling rate. Now, the only trick to watch out for if we do this calculation properly is that we have a scaling factor out the front here. This scaling factor comes from the fact that we have integral representations, so if we change the scale of omega, we get a correction term over here too coming out. The reason I mention this intuition is because when we do filtered design, we can see how we have to change the frequency specifications from continuous time to discrete time. I have presented here what is hopefully an intuitive explanation of what happens when x of t is band limited. The only remaining question to ask is, what happens if x of t is not band limited? That's when the theory of sampling comes in that we discussed in part 2. Our sampling result from part 2 can be expressed in the following form. If we have an arbitrary signal x of t, not necessarily band limited, going through our A to D converter, then through our D to A converter to get y of t, then we know from our sampling result that in the frequency domain, y of omega is obtained by low-pass filtering the infinite sum of the Fourier transform of x of t shifted to the left and to the right an infinite number of times. We, of course, only care about this initial part right now. Our question is, if x of t is not band limited, what's the relation between the Fourier transform of x of t and the discrete-time Fourier transform of x of k? As foreshadowed, we are going the long but simple way of getting to the answer. What we have here does not seem very helpful until we realise two key properties we have. Consider taking y of t and sending it back through this same system again. Because y of t is band limited, that's what this low-pass filter is doing, it means that if we send y of t through this system, then we get y of t coming out, the same signal. The second key property is that if we send y of t through this system here, then the samples y of k are equal to the original samples x of k. This is because our D to A converter is performing an ideal reconstruction as we described in part 2, and in an ideal reconstruction we know that the signal we're reconstructing agrees with the sample points, so we know that y at any integer time k is equal to x of k from the first time through the system. So y of t, when it goes in, we know that the sampled values agree with the input values at integer times. Therefore, we get that y of k is equal to x of k. The way to think of this is that I can obtain x of k by putting into the system y of t. This means that rather than put in x of t with a Fourier transform big X of omega, I can imagine that I'm putting into the system y of t with big Y of omega as the Fourier transform. Whether I put in x or y, I'm going to get the same samples x of k. But importantly, this latter choice, putting in y of t, gives me a band-limited signal, and I know from our previous result that if I put in a band-limited signal, then the discrete-time Fourier transform of x of k is going to be equal to the Fourier transform of the signal coming in. Therefore, the discrete-time Fourier transform of x of k is given by this expression here. Actually, to keep things simple, I've been talking about the discrete-time Fourier transform for values of omega between minus pi to pi. The reason I have been doing this is because it's the inverse discrete-time Fourier transform that's the more important object, because it gives us a representation of a discrete time signal as a sum of sinusoids, which is what we need. And the definition only looks at values of big X of omega between minus pi to pi. Indeed, the integral only goes from minus pi to pi. If we keep this non-standard viewpoint, then we can get rid of this low-pass filtering function out the front, because we only care about the value of x of omega between minus pi to pi, and the low-pass filter passes that value and blocks everything else. However, the rest of the world takes the definition of x of omega to be the discrete-time Fourier transform of x of k given by this formula here, and this formula will always produce a periodic x of omega. Therefore, by convention, if we say that x of omega is equal to something, and we do not specify that we're only talking about values of omega between minus pi to pi, we have to assign it to something that is periodic with period 2 pi. This means that if we remove this restriction here, then this expression is wrong. The low-pass filter will set the values of this guy to 0 outside of minus pi to pi, so it will certainly not be periodic in general. However, the infinite sum here is periodic with period 2 pi, and because it gives us the correct answer for omega between minus pi to pi, and because it's periodic, then the infinite sum on its own must be what the discrete-time Fourier transform is equal to. We therefore have that the discrete-time Fourier transform of omega is equal to this expression here, true for all omega. And this is true regardless of whether or not x of t is band limited. If x of t is band limited, then this is still the correct answer. The previous page, which did not have this infinite summation here, is only true if omega is restricted to being between minus pi to pi. As soon as we want it to be true for all omega, which normally we do want that's what the rest of the world does, then this is the correct answer here. However, remember that we only care about the values between minus pi to pi, so this looks more confusing than it really is. The simple explanation is that when x of t is band limited, then the discrete-time Fourier transform is equal to the Fourier transform. That's not precise, it's actually equal to this periodic replica, but we only care about one period of it here, and so intuitively I like to say that this is equal to this for simplicity. To conclude, remember we are interested in a system where our continuous time signal comes in, it gets sampled to produce a discrete time signal, we process x of k using some digital signal processing algorithm that produces y of k, which we put through a D to A converter to get our signal y of t. And we realized that we can understand this system going from xt to y of t by looking in the frequency domain. In particular, if we know what our digital signal processing algorithm does to go from x of k to y of k in the frequency domain, meaning we know the relationship between the discrete-time Fourier transform of x of k to the discrete-time Fourier transform of y of k, then we can easily deduce the relationship from the Fourier transform of x of t to the Fourier transform of y of t. And we do this in the following way. When we sample, it's the time domain relationship that is very easy to write down. If our sampling period is 1, then we simply have that x of k in discrete time is given by x of k in continuous time. The more complicated formula is the expression for x of omega in terms of x of omega. We now know though that in the frequency domain we have this relationship here. Our DSP block will process x of k and do something to it, and if we understand it in the frequency domain, then we can work out what happens when we go through to the D to A converter. This time, the time domain relationship is the more complicated one, but we have a straightforward frequency domain relationship between the input and the output. At the start of this chapter, we explained that if we've got e to the j omega naught k going into our D to A converter, then provided omega naught is between minus pi to pi, then the signal coming out is just given by replacing k by t. And so this means that the Fourier transform of y of t is just given by low-pass filtering the Fourier transform, the discrete-time Fourier transform of y of k. The only reason we low-pass filter is because the discrete-time Fourier transform is periodic with period 2 pi, but we only care about the values between minus pi to pi, and our output signal needs to be band limited. Therefore, this is the correct thing to do. If we did want to write down an equation for y of t, that would be given by sinc interpolation that we discussed before. If, for brevity, someone asks about the relationship between the Fourier transform and the discrete-time Fourier transform, then they have this picture in mind here of how we go from a continuous time signal, we sample it, we then process it, we go back again, and we want to understand from the Fourier transform to the discrete-time Fourier transform what happens when we sample, and that's given by these two equations here in the time domain and frequency domain. And then when we finish processing our signal, we want to go from our discrete time signal back to a continuous time signal, which we do by reconstructing it. That's given in the time domain by sinc interpolation, but in the frequency domain it's just given by this simple formula here. We come now to looking at the discrete Fourier transform and the inverse discrete Fourier transform. They are given by these equations here. They are for working with a finite sequence of numbers. Specifically, given a vector of n elements in the time domain, the discrete Fourier transform gives us a vector of n elements in the frequency domain, and we can recover our original sequence by taking the inverse discrete Fourier transform. Compared with the discrete time Fourier transform, there are two differences. The first is that the infinite sum has been replaced with a finite sum, and the second difference is that the arbitrary frequency omega has been replaced with a discretized frequency or sampled frequency of 2 pi w on capital N. Here 2 pi is just converting between angular frequency and ordinary frequency. Both x of w and x of n are periodic with period capital N. This is because we have sampled in both the time and the frequency domain. More will be said about sampling presently, but remember, when we sample in one domain, we create a periodic structure in the other domain. Since we've sampled in both time and frequency, both time and frequency are therefore periodic. Perhaps the only other thing to note initially is that the inverse discrete Fourier transform representation is representing our finite sequence x of n by a sum of sinusoids. So it's in the same spirit as all the other Fourier transforms. Let's now look at how this fits in with our bigger picture. Our end-to-end system that we have been considering throughout looks like this. This of course assumes that x of t goes on forever, and so x of k will be doubly infinite, with k going from minus infinity to infinity and so forth. But of course in practice we're only going to have a finite amount of data to work with. Even if we have lots of data available, often we want to break it into manageable chunks and work with each chunk at once. We've mentioned several times now that our ears perform a Fourier transform, but they don't perform an actual Fourier transform because that would require them to wait for an infinitely long time to collect all of the signal and then decompose it. Rather, they are performing what we refer to as a short-time Fourier transform. Intuitively, sound is going to change its characteristics over time, and we want to have some sort of a Fourier transform for the period of interest, not over the whole period of the signal, and the discrete Fourier transform allows us to do this. A caveat is that later we may learn that we should be windowing the data beforehand, but for now the concept is this. We have a finite amount of data, we want to work out what is its frequency content. Here is a finite amount of data. What would its frequency content be? When viewed like this, it is very tempting to fit a sinusoid through these data points and then say, oh yes, these data points represent the frequency of this yellow sinusoidal curve. We will not obtain this yellow curve though if we try to fall back to our existing tool of the Discrete-time Fourier Transform. Indeed, if we try to force the use of the Discrete-time Fourier Transform, much like one may use a hammer on all problems, if we try to force the use of the Discrete-time Fourier Transform to work out what the frequency content is of these finite amount of data points, what we're forced to do essentially is to say that because I only have a finite amount of data here, I need to replace my limits to go from k equals 0 to 1, 2, 3, 4, 5, 6, 7. If we therefore replace the limits of our summation for k equals 0 to 7, and we take these green sample points to be the values of our x of k for k equals 0 to 7, then we do find a frequency spectrum here, but what of? Well, we know what it's of. It's going to be of whatever the inverse Discrete-time Fourier Transform is of this equation here. We can work out what x tilde of k looks like by using the following reasoning. When we changed our summation to go from 0 to 7, that means that we are implicitly setting all other sample values to 0, going off to the infinite future and going back to the infinite past. If we want to visualize what the continuous time version of this signal looks like, where our sample points are 0, 0, 0, then in this nice sinusoid here, and then 0, 0, 0, then we perform sync interpolation through all these points. Now, I haven't done this on a computer, so my guess is going to be completely wrong, but here is my guess as to what it might possibly look like, and the key point here is that it does not look like this original sinusoid here. To summarize, if we take our green sampled points here and ask what is their frequency content, then intuitively we want to fit this yellow curve to them, which is a nice sinusoid, and say that this is the frequency of these points. If, however, we fall back to using the Discrete-time Fourier Transform, then with a lack of knowledge of what else to do, we're forced to set all the other values to 0, compute the frequency spectrum of that signal, and we can actually work out what signal we're computing the spectrum of, and it's this blue curve here which disagrees with our yellow curve there. We will pull out a component with the same frequency as the yellow curve, but we'll also have higher frequencies there due to this discontinuity of going from zeros to a single period of a sinusoid back to zeros. While there may well be situations when we do want to assume that our signal is 0 outside of where we have recorded our data, often we're in the situation of wanting to recover this nice yellow curve here. So if setting the signal to 0 outside of this region appears to be the wrong thing to do, how else could we extend this signal to end up with this nice yellow curve here? Well, visually looking like this, we see that all we need to do is extend it periodically. We just take our data points here and replicate them forwards in time and backwards in time. Performing this periodic extension is precisely what the DFT is implicitly performing. We will now make this mathematically rigorous. We are given a finite amount of data in the time domain. From this data, we then create a periodic extension x of k, where x of naught's just x of naught up to x of n minus 1. Then going forwards, we repeat our sequence an infinite number of times, and going backwards we also repeat our sequence an infinite number of times. We can then apply the Discrete-time Fourier Transform to x of k. Because we have extended this periodically, then we hope that by looking at the frequency domain content of x of k, we can work out what are the fundamental frequencies in our finite amount of data here. When we come to compute the actual Discrete-time Fourier Transform, we find two interesting things. The first is that because we have a periodic structure here, in fact, these are going to keep adding in here, and we end up with values of infinity in here. But we can deal with that by replacing them with Dirac delta functions. We also find that values of x of omega are going to be 0 except for these occasional Dirac delta functions that occur at regular intervals. We saw earlier that if we sample in one domain, we create a periodic structure in the other domain. Well, the reverse is also true. If we have a periodic structure, then in the other domain we have a discrete pattern, a discrete structure. Whenever x of omega is non-zero, it's actually going to be a Dirac delta function. And so therefore, if we just ignore the Dirac delta function and look at the magnitude, the number out the front multiplying each one, we can just say that this is the frequency content of x naught to x of n minus 1. And that is all that the DFT is doing. We are now ready to summarize. Given a finite amount of data, we can form the discrete Fourier transform. Its only purpose in life is to tell us what coefficients we need to be able to represent our data as a sum of sinusoids in this form here. And this on its own is already useful. It gives us a frequency decomposition of x naught to xn minus 1. We've written it as a finite sum of a finite number of complex exponential sinusoids. On the one hand, that could be the end of the story. But then we also want to know, how does this fit in with the processing of continuous time signals and with the discrete time Fourier transform, which is what happens when we sample a continuous time signal. So to complete the story, we also look at the correspondence between the DFT and the discrete time Fourier transform given by a periodic extension of our data here. The reason for the periodic extension is because it's the only way to make the two match. If we take the discrete time Fourier transform of our periodic extension, then we get big X of omega, which we can substitute in to our inverse discrete time Fourier transform to get a representation of x of k. Now x0 to xn minus 1 is just a single period of x of k. So if we simply replace k by n, we get that the inverse discrete time Fourier transform also gives us a Fourier representation of our data samples here. So one can naturally ask, what's the relationship between this inverse discrete time Fourier transform representation of our data here, obtained by using a periodic extension of it, versus just using the inverse discrete Fourier transform representation? Due to the periodic nature of x of k, we find that its discrete time Fourier transform is represented by a sum of Dirac impulses. I just have a proportional symbol here because I don't want to worry about the factor of 2 pi on n out the front. So because we have a periodic time domain structure, we have got this comb-like or sampled structure in the frequency domain. These Dirac impulses are going to convert the inverse discrete time Fourier transform, convert it from an integral to a sum in here. The only other trick to realise is that because x of omega is periodic with period 2 pi, we are free to change the limits of integration. Originally they are from minus pi to pi, we can change them to 0 to 2 pi without affecting the representation here. So if we change the limits from 0 to 2 pi, and if we substitute in this pulse train of Dirac impulses into here, this integral becomes this summation here, showing that indeed the discrete Fourier transform calculates the same spectrum that we would get had we extended our original signal periodically and taken the discrete time Fourier transform. The only difference is that the discrete time Fourier transform gives us these Dirac delta functions, but we want to throw away the Dirac delta functions and just keep the magnitudes out the front. This is precisely what the discrete Fourier transform is doing for us. A Fourier series is another Fourier representation of a continuous time signal. Here, the Cn are arbitrary complex numbers, and the summation is called a Fourier series. We are just summing an infinite number of complex exponential sinusoids weighted by C of n. This produces a periodic signal. X of t will be periodic with period 1. Of course, we can apply a scaling factor here to change the periodicity over here, but for simplicity, I'm considering the normalized case here. Apart from a scaling factor of divided by big N, this looks very much like the inverse DFT representation which we used just before to represent a finite amount of data. In fact, essentially the only difference is that this summation here goes from minus infinity to infinity rather than just for a finite block. This then converts our representation from being representing a finite number of samples to representing a continuous time segment of data. We can think of this as representing x of t in the interval 0 to 1. Outside of this interval, x of t is given by periodic extension. We can think of the Fourier series as just being a special case of the Fourier transform. Indeed, we can obtain the same signal x of t using an inverse Fourier transform representation in the following way. In yellow, we have the standard inverse Fourier transform. If we replace angular frequency with frequency, we get this expression here in green. And comparing this expression in green with our Fourier series here, we see that they match up if we choose our x of 2 pi f to be a pulse train of Dirac impulses to convert this integral to a summation here. In one direction, we see that a periodic signal x of t has got this sampled-like or comb-like structure in the frequency domain. In the other direction, we know that if we start with an arbitrary signal and look at its Fourier transform and then sample it in the frequency domain by keeping only the values of its frequency content at uniformly spaced samples, then the inverse Fourier transform of this sampled version is going to be a periodic signal. And so therefore we can treat the Fourier series representation as being what we get when we sample the Fourier transform. Since sampling is equivalent to a signal being periodic, equally well we can consider the Fourier series as a Fourier transform representation of a periodic signal. Now, why have a representation of a periodic signal given by both a Fourier series and a Fourier transform? Well, there it's a matter of convenience. If we use the Fourier transform, we have these ugly Dirac delta functions everywhere. By using the Fourier series, we don't have to deal with these functions that are not really functions and worry about the mathematical difficulties that go along with that. We have now discussed 4 frequency domain representations of signals. We can take a Fourier transform, a discrete-time Fourier transform, a discrete Fourier transform, or we can form a Fourier series. However, it's important to realize that in each of these 4 representations, the concept of frequency is one and the same thing. By frequency, we always mean a component of the form e to the j omega t. Now, t can be discrete time or continuous time, but a frequency component is always of this form here. And of course, omega can be 2 pi f, angular frequency or frequency in hertz. Let's look at these 4 representations individually before discussing their similarities and differences. The Fourier transform representation is given by this integral here. These are the frequency components. Here are our sinusoids, and it gives us a representation for a continuous time, infinitely long, aperiodic signal. Now, it could be periodic. If it were periodic, we'd have Dirac delta functions in here. Be a bit careful about when people talk about the existence of this representation. If you're talking from a mathematical perspective, then you cannot represent periodic signals if you want this integral to exist in the usual sense. But you can represent periodic signals if you permit generalized functions such as Dirac delta functions in here. Since this course is about engineering, I'm going to be quite liberal when I talk about integrals existing or not. Don't be confused if you then later take a maths course and find that things don't always exist. Moving on, the discrete-time Fourier transform is for representing discrete-time, infinitely long aperiodic signals. It's given by this integral expression here. These are the frequency components, and these are our sinusoids here. Just like for the Fourier transform, x of k might be periodic, but then x of omega would have to contain Dirac delta functions. The discrete Fourier transform is for representing a discrete time and finite signal. Here we have x naught to x capital N minus 1. Alternatively, we can think of this as representing a periodic signal. Given a finite signal, we can always extend it to be infinitely long simply by repeating it. So we have x naught, x1 up to x big N minus 1, then x naught, x1 up to big X N minus 1, etc. The reason why we mention a periodic signal here is because it's this periodic perspective that allows us to connect the DFT with the other frequency representations on this page. Finally, we have a Fourier series representation which represents a continuous time periodic signal. We could of course think of it as being finite if we looked at a single period. As we mentioned before, the first common feature is that they are all a sum of sinusoids of the form e to the j omega t. Here's e to the j omega t explicitly. Here is e to the j omega k, but k is just time, so that's basically e to the j omega t again. Down here we have e to the j. Now here we've got our time, which is n, so that's the t part, and our omega, our frequency, is given by 2 pi w divided by n. It's a sampled frequency. This is also of the form e to the j omega t. And over here, the same thing, e to the j, omega is sampled at 2 pi n times t. All of them are just giving us a sum of magnitudes and phases multiplied by e to the j omega t. This is a frequency domain representation, and we're representing frequency by these complex exponential sinusoids. It's that simple. Another thing to appreciate is that if you're the sort of person who likes just having a hammer in your toolkit, then you can do everything with just the Fourier transform. If we want to represent a discrete-time Fourier transform using a Fourier transform, all we need to do is set our x of omega to be 0 outside of minus pi to pi, and we recreate this expression down here. If we want to represent a DFT using the Fourier transform, then again we can do this by using Dirac delta functions in here to convert this integral into a sum. And over here, for our Fourier series representation, once again, if we use Dirac delta functions in here, we can make this integral into a sum. So the only reason we've got 4 different representations is the same reason why, if you're good at woodwork, you use more than just one saw. You've got different saws for different purposes. You could do everything with one saw, but it's just inconvenient. To elaborate, if I have a periodic signal, either continuous time or discrete time, if I used a Fourier transform representation, I'd have to have Dirac delta functions. I avoid having Dirac delta functions by using either this representation for a continuous time signal or this representation for a discrete time signal. The reason for using the discrete time Fourier transform rather than just sticking with the Fourier transform is similar. It avoids having Dirac delta functions, but this time they would appear in the time domain rather than the frequency domain. Remember when we discussed sampling that given a discrete time signal, if we wanted to take its Fourier transform, we'd have to convert all our samples into Dirac impulses. The discrete time Fourier transform is exactly the same as the Fourier transform on a sequence that we create by adding Dirac impulses. Indeed, here is our Fourier transform. If we take our pulse train form from samples and we substitute this into here, these Dirac delta functions convert this integral into this sum here. So the discrete time Fourier transform is just the Fourier transform applied to our sampled signal, meaning we've added Dirac impulses to each of the sampled values. These 3 representations are simply alternative forms of the Fourier transform where we have eliminated Dirac delta functions for convenience. Sometimes we intentionally convert one type of signal to another type of signal. The most common case is that because we want to do digital signal processing, we start off with a real-world signal x of t and we sample it to get x of k. If we do this conversion using an analog to digital converter, and then we process our signal x of k to get y of k, we then want to convert y of k back into a continuous time signal y of t, and we want to understand the relationships between the different frequency representations here. Precisely, we are asking, if we take a signal x of t and we put it through an analog to digital converter to get x of k, how have we altered the signal in the frequency domain? There has been an alteration for the simple fact that we've gone from a continuous time signal to a discrete time signal. I cannot immediately take the Fourier transform of x of k because that's undefined. The trick we did before was convert x of k into a train of Dirac delta functions and took the Fourier transform of that. Equivalently, we can just take the discrete-time Fourier transform of x of k. Both methods give us the same answer. The answer we get, x of omega, is going to be the frequency domain representation of our sampled signal. So we're asking, if we take a signal x of t with a frequency domain representation given by x of big omega, and we sample it, what is the frequency domain representation of x of k? That is, what is capital X of small omega equal to? The answer is that we obtain this x of omega by taking our original x of omega and making it periodic according to this infinite sum here. We can give a very intuitive reason for why this equation is true. For our x of k, we need to construct it using only frequency components between minus pi to pi. In this integral here, these are the only frequencies we're allowed to use to reconstruct x of k. Let's assume my original signal x of t is a single sinusoid at frequency omega, which is limited to being between minus pi to pi, plus 2 pi m, where m is some integer, maybe m equals to 10, it doesn't matter, times t. If we were to sample this signal x of t, we are going to get a signal x of k. When we come to represent x of k using this integral expression here, we cannot get to this frequency here because it's outside of minus pi to pi unless m equals to 0. So the way we have to get to our sample points x of k is by using other frequency components, frequencies between minus pi to pi. Now, just by inspection, we actually see that at integer samples, when t is an integer, e to the j 2 pi mt is always equal to 1, which means that we can just cross out this term, and in this representation here, we can just use the fundamental frequency e to the j omega t. Mathematically, the frequency domain representation x small omega is equal to 2 pi Dirac delta function to pull out the frequency at omega. I've added a prime everywhere so you don't confuse it with this free variable omega over here. Substituting this into this representation here gives me an x of k that agrees with my original signal x of t up here. Because this argument that we made is true for any value of m, we see that we have lots of frequencies that get mapped back to this single fundamental frequency between minus pi to pi. And this infinite summation here is simply doing this mapping. It's saying whatever frequencies I have outside of minus pi to pi need to fold back in to a frequency between minus pi to pi. That is all this is saying. Asking about the relationship in the reverse direction simply means what happens if we pass our signal x of k through a digital to analog converter. What happens in the time domain and what happens in the frequency domain. The D to A converter has a choice to make. When we sampled x of t, we threw out information. When we go from a discrete time signal to a continuous time signal, we need to add information back in, and there's an infinite number of ways we can do this. By convention, though, what we do is when we reconstruct a signal, we assume that the original signal is band limited. We don't have to do this. For special applications, perhaps we can do something different, but normally this is the assumption we make, so therefore if we're not told anything to the contrary, then we understand that to go from a discrete time signal to a continuous time signal means that we interpolate our points on the assumption that x of t will be band limited. If we sample a signal e to the j omega t, and provided omega is between minus pi to pi, when we sample it, we simply get e to the j omega k. We just replace t with k. So the reconstruction procedure is very straightforward. Wherever we have e to the j omega k, we just replace it with e to the j omega t. This way, from this discrete time Fourier transform representation of x of k, we recover x of t simply by sending frequencies e to the j omega k to e to the j omega t. We go from discrete to continuous. We therefore immediately get that x of omega in the Fourier transform domain is given simply by x of omega in the discrete time Fourier transform domain, simply because e to the j omega k gets mapped to e to the j omega t when we go from discrete time to continuous time via interpolation. If we have a set of points, discrete points, that are fitted by e to the j omega k, then to get the sinusoid that passes through these points, we just promote k from discrete time to continuous time. It's that simple. So we've got x of omega is equal to x, the other x of omega, for omega between minus pi to pi. Outside this region, we don't want to have any frequency components because we're trying to reconstruct a band-limited signal. So outside of this region, x of omega is equal to 0. Now x of small omega is periodic. Therefore, we do not have that the two x's are the same for all omega. It's only true for omega between minus pi to pi. And outside this region, the Fourier transform x of big omega is going to be equal to 0. In other words, we obtain x of big omega by low-pass filtering x of small omega, if you wish. But remember, we are not in the same space, so that's not strictly correct. But we are chopping off x of omega to go from the discrete time Fourier transform space to the Fourier transform space. We have now summarised how we can go from the Fourier transform to the discrete time Fourier transform and back again. That needs clarification. What does it mean to go from Fourier transform to discrete time Fourier transform? Implicitly, whenever we say that, we mean that we're going to sample our signal to come here, and when we go back, we reconstruct it using a D to A converter. Moving on, what does it mean to ask about the relationships between the discrete time Fourier transform and the DFT? In my mind, I can think of two interesting ways I might want to go from a discrete time infinitely long signal to a discrete time finite signal. The first way is that I have my infinitely long signal here and I simply draw a region around a small part of it and say, I'm interested in these samples here, what can we do with them? Another interesting thing, academically speaking at least, we can say that we have our infinitely long sequence. In the frequency domain, it has this frequency representation, which is periodic with period 2 pi. What happens if we were to uniformly sample in the frequency domain to compress the information in our signal, for example? What would result? In case 1, there is no easy relationship. Indeed, we have discarded an infinite amount of data on either side here, and so the discrete Fourier transform doesn't tell us very much about the original discrete time Fourier transform. What we can say, though, is if we go in the other direction, the signal that we are going to reconstruct is what we would obtain if we took these samples here and repeated them on either side infinitely far. In other words, we know that the DFT can be understood in terms of the DTFT by a periodic extension. So while situation 1 is something we are quite often going to do in practice, there is no obvious relationship. Case 2, there is a nice relationship. And indeed, notice that to go from here to here we sampled in time, and we mentioned that in case 2 we are now going to sample in frequency. So down here we have got a signal that maybe started off life as x of t, and it's been sampled first in time and then in frequency. This representation of x of n shows clearly that we have sampled in frequency. We see that we are only using frequencies of the form 2 pi w on capital N, where w is an integer. So we are not using arbitrary frequencies to reconstruct x, we are just using a finite number of uniformly spaced samples. A question we can ask for case 2 that does have a nice mathematical answer is, if I start off with my signal x of k, and I sample it in the frequency domain uniformly like this, then what is the relationship between x of k here and x of n down here? We know in the frequency domain what the relationship is. We have taken our frequency response and sampled it, keeping only a finite number of points and throwing out the rest. So that relationship is obvious. What's happened in the time domain? The answer, not surprisingly, is given by the same thing that happened when we went from here to here. Remember that when we sampled in the time domain, then in the frequency domain we got a periodic structure. Well, here, if we sample in the frequency domain, then in the time domain we get a periodic structure. We do not get the periodic structure just by isolating a small block and replicating it either side. Instead, the periodic structure comes from shifting and adding all the blocks of the original signal to form a periodic signal. We haven't explicitly derived this in this video series because this result is not used as often as the result from here to here, but nevertheless, by time-frequency duality, we have that this result holds. In short, what this result says is that if we take a discrete time signal x of k, if we compute its frequency representation using the discrete time Fourier transform, and if we then sample that representation keeping only n equally spaced samples between 0 and 2 pi, then if we form a signal by using just these frequencies here and using the magnitudes and phases given by what we sampled, if we form this signal here, then the signal we form here is related to our original signal that we sampled in the frequency domain by this relationship here. Having discussed how to go in this direction, we can ask about going from the DFT to the DTFT. Of course, first we have to ask, what does it mean to go from the DFT to the DTFT? We need to define that first before we can give an answer. Just as there were two interesting ways of going in this direction, there are two interesting ways of going in the reverse direction, only one of which has a nice mathematical description though in the other domain. If we take our discrete time finite signal, x0 to x capital N minus 1, and if we go back to an infinitely long signal simply by appending zeros on either side of it, we can certainly do that, but then we won't have a very clear relationship between the two frequency domain components. On the other hand, if we take our finite signal and we extend it to make it periodic, and this is something very natural to do, because if we look at this representation here, it automatically gives us x of n for any integer n, and it does it in a way that makes it periodic. So it's very natural to ask, given this description of x of n, if we just change n to k, then what's the relationship between x of w here and big X of omega here? Before answering this question, it's worth remembering that we said that the only reason we use these other representations is to avoid using direct delta functions up here, and so it's going to be the same thing down here. The relationship between this x of w here and this x of omega here is essentially that this representation of this signal here, this periodic signal, will have direct delta functions, whereas here we don't. We can derive the relationship between x of w and x of omega just by inspection. This integral equation is representing our signal using these frequency components, e to the j omega k. Down here we are forming our x of n by using e to the j 2 pi w over big N as the frequency components here. Choosing x of omega to be given by the sum of our x of w's here multiplied by appropriate Dirac impulses means that when we substitute this into here, this integral becomes this summation. The only thing to be careful of, and I'm not going to write it out, is that this equation here is true for omega between minus pi to pi, and because this x of omega is periodic with period 2 pi, then x of omega is given by this periodically extended to the left and the right. And we can write that in the usual way by having another sum out the front and just shifting this by 2 pi forwards and backwards infinitely often. To summarise, if we were to start with x of k and sample it in the frequency domain, then because in the frequency domain we already have a periodic structure, sampling a periodic structure just gives us a finite amount of data to work with because it's repeated forwards and backwards. So if we take x of k, sample it in the frequency domain, then we end up with a finite number of terms, call them x0 to x capital N minus 1, and if we then use this inverse discrete Fourier transform to get a representation of our signal, we find the relationship between this signal and this signal is given by our standard way of converting an aperiodic signal into a periodic one, which is taking this signal and adding to it copies of this signal shifted forwards and backwards by an appropriate amount and added together. In the reverse direction, if we have got a series of data points represented in this form here, then this representation already gives us a periodic signal here, and we can ask what is the discrete-time Fourier transform of this periodic signal, and the answer's given by this pulse train here, at least for omega between minus pi to pi, and then we extend this periodically because x of omega is periodic. As we said earlier, the only reason for having this representation here is to avoid having to use direct deltas in these representations up here. In fact, there's another reason for using the DFT, and that's on computers we can actually compute this very easily, at least for certain values of big N when we can use the fast Fourier transform. Before discussing in detail the other half of this circle, let's observe a basic structure. When we go from the Fourier transform to the discrete-time Fourier transform, we are going from continuous time to discrete time, therefore we are sampling in time. Similarly, when we are going from continuous time to discrete time here, so this is also a sampling in time. Diagonally opposites both have a sampling in time structure to them. On the other hand, when we go from the Fourier transform to the Fourier series, we are going from an aperiodic signal to a periodic signal. That corresponds to sampling in the frequency domain. And similarly, when we go from the DTFT to the DFT, we're essentially going from an aperiodic signal to a periodic signal, and that again is sampling in the frequency domain. So the cross diagonals, these two are sampling in the frequency domain, these two are sampling in the time domain. Given a Fourier series representation, then we already have a continuous time signal, so the only interesting question to ask, how is the Fourier transform of x of t related to the coefficients c of n? And as we saw earlier, when we went between the DFT and the DTFT, the answer is given simply by saying that x of omega is basically given by taking the c of n's and converting them to Dirac delta functions, thereby converting this integral here with the use of the Dirac delta functions, converting this integral here into this summation here. While in practice, the only time we go from here to here is if x of t is already periodic, and then we prefer a Fourier series representation to avoid the Dirac delta functions, we can ask the theoretical question, if we have an aperiodic signal x of t, and if we sample it in the frequency domain to get the sample c of n, then what's the relationship between our original signal x of t and our Fourier series representation x of t down here? And the answer has the same structure as before. Our new signal x of t is given by taking our old signal and just making it periodic by replicating itself an infinite number of times by shifting it to the left and the right. Put simply, everything we said about going between the DFT and the discrete-time Fourier transform can be applied to going between the Fourier series and the Fourier transform, because both of them can be understood in terms of sampling in the frequency domain. Not surprisingly then, if we want to understand about going from the Fourier series to the DFT and back again, well, this concerns sampling in time, and so expect exactly the same comments as when going from the Fourier transform to the discrete-time Fourier transform. We choose to go from x of t to x of n simply by sampling in the time domain. Because x of t, given by the Fourier series representation, is periodic, we don't need to sample it an infinite number of times because its samples anywhere are related to its samples in the first period here. Therefore, the DFT just operates on these finite samples in one period of the signal. Because we have sampled our signal, information has been lost. The only way to try to reconstruct the original continuous time signal is by making some assumption about it. The standard assumption we make is that it is band limited. That is, we assume that x of t here does not have any high frequency components. When we sample, we are blind to high frequency components, or more accurately, when we sample them, we can't tell the difference between a high frequency component and a low frequency component. They get aliased down. Our reconstruction procedure then simply says we want to keep these sinusoids in here. Although n here is a discrete value, I can replace it by time t to make it continuous, and thereby I get a continuous time signal, and that's our reconstruction procedure. A caveat is that I have written, for brevity, this Fourier series to have period 1. If we are really going from here to here, I need to change this to have period big N to match up. Going in this direction means, as we have been discussing, that I start with my signal x of t and I sample it. I can ask, when I go to reconstruct my signal, what am I going to get? If it is band limited, we are going to get the reconstructed version. If it's not band limited, then we know from our comments before that the high frequency components that were in x of t, when we sample them, they are going to be indistinguishable from lower frequency components, and so therefore our reconstructed signal will have, in a frequency domain representation, all its frequencies will have been collapsed down to low order frequencies. In other words, and assuming we'd written this to be periodic with period n, then if x of t is band limited, we simply have that x of w is equal to c of w. There's a one-to-one correspondence here, whereas if this is not band limited, then the higher order frequencies whose coefficients are given by c of n, where n is larger than big N or smaller than 0, they get aliased down to some frequency between 0 to big N minus 1. Precisely, we get this same periodic structure. All this summation is doing is taking our higher frequencies and mapping them back down into frequencies between 0 to n minus 1. So, if we sample x of t to get x of n, then in the frequency domain we have preserved all frequencies that lie between 0 to 2 pi, and all the other frequencies have been aliased down into a corresponding frequency between 0 and 2 pi. Having now finished our summary of part 3, it is appropriate to return to our opening 2 questions in part 1. By and large, digital signal processing means we start off with a continuous time signal, we sample it, we process it using digital signal processing techniques, we convert it back to a continuous time signal, and we hope that our DSP algorithms have transformed our signal from x of t into y of t in a desirable way. The 2 opening questions were, how can we work out what our DSP block does to this signal from x of t to y of t, and then how can we design our DSP algorithm to achieve a certain behaviour between x of t to y of t. Ignoring technical details, we basically have that if x of t is band limited, then the frequency domain representation of x of t is the same as the frequency domain representation of our sampled signal here, and when we go to reconstruct it, once again, whatever the frequency domain representation of our signal is at the output of our DSP algorithm will be the frequency domain representation of y of t. Therefore, in the frequency domain, we're simply operating on our signal from x of t to y of t in the frequency domain. Whether we do it in continuous time or discrete time, it's one and the same thing. In particular, if I want to bandpass filter my signal x of t, for example, then all I do is I construct a bandpass filter for my DSP algorithm. Whatever I do in the frequency domain here happens in the frequency domain out here. To end up with this very simple relationship, we had to be careful how we defined the frequency domain content when we were in discrete time. The Fourier transform equation operates on a continuous time signal. We cannot take a discrete time signal and shove it into the Fourier transform. It doesn't make sense. So we need to work out how to define what it means for a signal in discrete time to have a frequency domain representation. Ideally, however we define the frequency domain representation here, ideally it should be the same as the frequency domain representation out here. So the question is, how can we do that? And it turns out that the answer is we take our discrete time signal, we make it into a stream of Dirac impulses, and then we can compute its Fourier transform, and we find that it contains the band-limited part of the Fourier transform of x of t, and the only casualty is that it has been periodically extended on either side. However, we can get rid of those periodic extensions by low-pass filtering when we go through the D to A converter. Thereby, we end up with this very simple story that the frequency domain representation here and here is one and the same thing. That's the intuition. Rather than stay using the Fourier transform, which would mean that x of k here needs to be represented more like x tilde of t as a train of Dirac impulses, we instead want to use x of k, and so we develop the discrete time Fourier transform, which is just the Fourier transform, but done in such a way that we get rid of these Dirac delta functions so we can work with x of k directly and not with x tilde of t in here. When we are working in discrete time with the discrete time Fourier transform representation, its integral is only between minus pi to pi for the inverse discrete time Fourier transform. Therefore, we are only looking at frequency components of x of k that are low frequency, which means we can ignore all these higher order frequencies here. So this is a theoretical result. It tells us what would happen if we attempted to put in a signal here that was not band limited, but in practice we're not going to do that. We're going to put in a band limited signal, which means that the frequency domain representation here is the same as the one here. While there's a lot of maths behind it, and some of that's required in order to try to work out how to build a good D to A converter, when it comes to DSP itself, we get a very beautiful end result. If we want to filter our signal x of t to y of t, we just filter it in this domain here, and there's a one-to-one correspondence between frequencies, so therefore if we want a bandpass filter, we just build a bandpass filter. If we want a low-pass filter, we build a low-pass filter, and so forth.